which stands for Java Virtual Machine, is a part of JRE because JVM instance gets created during the runtime execution of your Java application and not during the development or when you compile your Java code. Even if you don't download the JDK package and just download the JRE package, you will still be able to create the JVM instance and run your Java application. So when does JVM gets created exactly is on the call of Java command, right? So when you call the Java command over the name of your .class file, then the JVM instance gets created and it invokes the main method. It is JVM which invokes the main method of your Java application. Just a quick overview what happens when your javac command is executed. So basically when you execute javac command, which invokes your Java compiler, and it creates a .class file which contains the bytecode representation of your Java code, right? And then what happens when Java command is executed? As I've mentioned, JVM instance will get created and the main method of your Java class gets invoked. So something like this. So first you compile your Java code and then you execute this Java command and the JVM instance will get created and your main method will get invoked and executed. Like you see here, the hello world which is inside the main method of your class is getting printed out. So what happens in between? So you execute the Java command, your JVM instance gets created and your main method of your class gets executed, but there is a series of steps which takes place after the JVM instantiation and invocation of your main method. So we're going to see those steps. In order to understand it, we need to understand the JVM composition. What does it consist of? So it consists of primarily class loaders, memory areas, execution engine, native method interface, and native method libraries. We are going to discuss each of them. Before that, here is the diagrammatic representation of the JVM composition, which will help you to remember it. So just have a look at this. Okay, so coming on to the class loaders. So class loaders is basically responsible to load the bytecode which is there inside your .class files into the method area of JVM. So method area is one of the memory area inside JVM which we are going to discuss, but for now just remember that class loaders are the ones which is going to load the bytecode which is there in the .class file, and it will save that data into the method area. There are three types of class loaders, and there have been some changes in the class loaders since Java 9. So first we'll discuss about the class loaders which were there up till Java 8. So they were primarily bootstrap class loader, extension class loader, and application or system class loader. Okay, so bootstrap class loader, what does it loads? So we'll look into that. So bootstrap class loader is primarily responsible to load the classes which are inside the rt.jar, and that rt.jar is inside the JRE lib folder. So if I want to show you that then if you see this Java JRE, so you have a lib folder. If you go inside that, you will find this. So boot is, and this rt.jar contains the .class files which are are basically the classes of your Java standard edition library. Okay, so these classes are primarily loaded by the bootstrap class loader. Okay, then comes the extension class loader, which I talked about. So extension class loader primarily loads the classes which are inside the jars, which is inside the jre-lib.ext folder, right? So these classes are loaded by extension class loader. Then comes your application or system class loader. So this application and system class loaders loads the classes which are the user defined classes which are there on the class path, and you define the class path while invoking the Java command. So system or application class loaders goes to that class path and loads all the .classes files on that class path, right? So this was up till Java 8. Since Java 9 we don't have rt.jar because Java 9 introduces the modularity, right? So you don't need to include all rt.jar classes. Instead they have been modularized based on their features. So if you see this is OpenJDK version 17, and there you will see a jmods folder, right? So if you go inside this jmod, you will find a lot of Java modules here, right? So so whatever was the content of the rt.jar now has been modularized into these Java modules. So coming back, bootstrap class loader, yes, it still exists in Java 9 and higher versions, but it does not load all the classes which are in all these Java modules. Primarily it is responsible to load that java.base.jmod, right? And as I said, if you see this, extension class loader does not exist since Java 9. It has been replaced by platform class loader, and it is the responsibility of platform class loader to load the other classes which are in the other Java modules which you see here inside jmods. Okay, then comes the application system class loader. Yes, it still exists since post Java 8 also, and its responsibility is also same. It's gonna load all the classes which are there on your class path. So these are the different class loaders. But since we have different class loaders, so comes a question, which class loader, and we have seen what each class loader loads, but still there is a question, which class loader will be invoked first, right? Or in which order they will be invoked. So let's see that. So whenever there is a request to load any class, then that request first comes to application class loader, but it does not load that class. It rather delegates that request to the extension class loader. So you see this blue arrow, okay, it signifies the direction of delegation. So the request gets passed from application class loader to extension class loader to load the class, but extension class loader again passes that to bootstrap class loader to load the class. So it is the bootstrap class loader which makes the first attempt to load the class, okay, by looking in whatever jars it is supposed to look at. If it is able to load that class, the class gets loaded. Otherwise it passes on that request again again to the extension class loader. So now you see this orange arrow. So now extension class loader tries to load that class. if it is able to load the class, fine, the class gets loaded. Otherwise it passes on that request to load the class again to the application class loader. Okay, so the extension class loader passes that request to application class loader. Now application class loader makes an attempt to load the class. If it is able to load the class gets loaded. Otherwise you come across class not found error, a very common error which we see when the application is coming up, right? So that class not found error comes during the class loading phase. Okay, now this class loading phase has been further divided into 3 phases called loading phase, linking phase, and initialization phase. So now we are going to see these phases. So loading phase first. So basically loading phase, it reads the byte code which is there inside your .class files and saves it in the method area. Fine. And it also saves a few of the class metadata, which is like a fully qualified name of the class and its immediate parent class, only immediate parent class. It also saves the information like whether that dot class is related to a class or an interface or an enum, right? And then it also saves the information about your modifiers, your access modifiers, variables, and other method level information, right? And finally it creates an object of type class to represent that .class file which it is loading, and it saves that object of type class inside the heap, not the method area. Okay, so it saves that object of type class to represent the file it is loading inside the heap, and we can access this object by calling the get class method, okay, on the of the object class. Fair enough. So this all is done during loading phase. Then comes the linking phase. Linking phase. Okay. Then comes the linking phase. The linking phase again is divided into verification, preparation, and resolution. So let's see what it does. So in verification, basically what is done is that correctness of that .class file is evaluated, whether it is in proper format and whether it is generated by a valid compiler. So all this is evaluated, and it is done by bytecode verifier. And if it is not successful and it is found that the .class file is not in proper format or it is not generated by a valid compiler, then you come across that java.lang.verify error. So this error comes during the verification subphase of the linking phase. Then comes the preparation phase. In the preparation phase, memory is allocated for the class level variables, okay, and that memory is initialized to the default value. So what I mean by that is, suppose in your class you have something like public static boolean my flag is equals to true. Okay, so in the preparation phase the memory will be allocated for this boolean variable, plus this boolean variable will be assigned the value as false, which is the default value of boolean type, not true, what we have written in code. It will be assigned false in the preparation phase. Then comes the resolution phase. In resolution phase, symbolic references for the type is replaced by direct references by looking at the you can say the method area area and identifying the referenced entity. So what I mean by that is, suppose in your class you are making a reference to some other class. So your class A makes a reference to some other class B. So in the resolution phase, what happens, the class A has been loaded, the class B also has been loaded, and now in the resolution phase, when your class A is trying to make a reference to class B, the symbolic reference or reference will be removed and actual direct reference will be established between class A and B. Now what happens is, sometimes it happens that there are two versions of class B which gets loaded, because that class B is coming from some jar and you have two versions of that jar. So there are two versions of that class B. What will happen now? How will the direct reference will be identified? So it won't get identified. It will be an ambiguous situation for JVM. So in that case, you come across class nodef found error. Okay, so when you see this class nodef found error, there are high chances that it is due to the resolution of the direct references, which is done in resolution phase. Okay, then comes the initialization phase. In the initialization phase, the static variables are assigned values. What do I mean by that is, so we see in the preparation phase you had public static boolean my flag is equals to true, and in the preparation phase memory was allocated and your my flag was assigned a value as false, which was a default value. In the initialization phase, your actual value which you have put in the code will be assigned. So after initialization phase, the value of your my flag will be true. Okay, this is a diagrammatic representation to help you remember about the class loading phases, so you can look at that. Then comes the memory areas. So there are different memory areas inside JVM responsible to hold different data, and they are used in different stages of your application run. So the first memory area there is method area, which we have already talked about. It saves the class's information, its metadata, its code and all, right? Including these class level or static level variables, object references and all, right? And it is a shared area. I mean, it contains the shared resources. Okay. Prior to Java 8, this method area was a part of PUMGen space, right, which was inside JVM only. But since Java 8, this method area is a part of a meta space which resides outside the JVM. Okay. Then comes the heap. Okay. One more thing, when I'm talking about method area, I talked about it. It holds the class code, method code, constructor. It also holds the runtime constant pool. Okay. Now coming on to the heap. So heap basically contains all the objects which gets created during your application runtime. Okay, and it is again a shared memory area. Okay, and one important thing I would like to mention here, suppose if in your class you have written something like public static class B reference B is equals to new class B, though it is static, then also the object of class B will be there in the heap, and the reference with the static reference with which you are pointing, which is there in your class A and you are pointing to class B, that reference will be there in the method area. Okay. Then comes the thread stacks. So thread stack, so each thread has a private JVM stack. Okay, and thread stacks contains multiple JVM stacks, and each JVM stack is dedicated for a particular thread. Okay, so whether or not you spawn any thread in your Java application, there is always a main thread which runs your application. So there will be a JVM stack for that main thread, and it will reside inside this thread stack. Okay, then each JVM stack, or you can call a thread stack for a particular thread, has multiple frames. Okay, and what are these frames? So these frames are getting created when your thread is invoking any method. So it invokes method 1, then it invokes method 2, then 3. Then there will be 3 frames inside your one thread stack, or a JVM stack which is dedicated for this thread. And each frame is going to consist or hold the variables or any reference which is specific to that method, right? And once your method execution is over, that frame will get destroyed. Okay, so these are the things to remember about frames. So multiple frames inside one thread stack or JVM stack, and there is one thread stack or JVM stack for each thread, and your thread stack's memory area consists of multiple thread stack or JVM stacks. Okay, then comes your PC registers. So PC register is per thread. Okay, so n threads, n PC registers. So in what do they store? They store the address of the available or current JVM instruction which is being executed. Okay, then comes the native method stacks, which are also called the C stacks. This is again per thread, and they store the method calls to native methods. What do I mean by native method? Is some method which is there in some class, and that class is written in some other programming language other than Java, which can be C, C++, or any other programming language. Okay, so now so method area I talked, it's a shared, it contains the shared resource, heap contains the shared resource, but thread stacks, which contains multiple thread stacks or JVM stacks, they don't contain any shared resource. They only contains the data which is specific for that thread. Okay, fair enough. Let's move to execution engine. So execution engine consists of primarily interpreter, JIT compiler or just-in-time compiler, and garbage collector. What is interpreter? So up till now we have seen that your .class file, its content is loaded and saved in the method area by class loaders. That content is in the form of a bytecode, right? But JRE is specific to the platform on which it is running, right? So if the platform, by platform I mean the operating system. So if you are running your application on Windows platform or your Linux platform, okay, so the bytecode will be same, but that same bytecode needs to be converted into machine code, and that machine code is specific to the platform, right? Because machine code needs to be understood by your Linux platform, and a different machine code is required to be understood by your Windows platform. Okay, so the process of converting that loaded bytecode into the machine code is done by interpreter. Okay, so yeah, so when you run your program, first your bytecode gets converted into machine code, and then it's executed. Just-in-time compiler, it is there for the performance of your application. So consider a scenario where a few lines of code is getting executed again and again, right? And its frequency of execution is too high. Then interpreter will again and again try to interpret that bytecode into machine code, and then it will get executed. So instead of that, what happens is, when a threshold of any line of code it gets reached, which is getting executed again and again, that few lines of code gets pre-compiled, or that's get compiled from the bytecode into the machine code by JIT compiler, and it gets, that machine code gets saved into the JIT compiler cache. And next time again when that code has to be executed, rather than interpreter converting the bytecode into machine code and then it getting executed, this step won't be there. That directly that machine code will be looked up from the, or in the JIT compiler cache. Okay. Then comes the GC, or the garbage collector. So what happens is, it's in a form of a daemon thread which keeps running throughout your application lifecycle, and its responsibility is to destroy or remove the unreferenced objects from your heap space. Okay, so this was it. And then, okay, native method interface. It is something like, it allows your Java code to interoperate with application or some libraries which are written in some other programming languages. So suppose your Java codes needs to invoke any method of a class which is written in some other programming language, then also it is possible through Java method interface. Okay, so using this you can invoke that, and whatever these libraries I just talked about, which are written in other programming languages and needs to be used by your Java application, they are on these native method libraries. Okay, so this was an overview of the JVM architecture and few of the important points. In the subsequent tutorials we will deep dive into each of the section, and we'll try to analyze them further. Okay, thanks a lot, friends.